Berlin, April 22nd, in 1945, 02:47 a.m. A German infantryman flattens against shattered brick. Soviet boots grind closer through rubble 20 meters, maybe less. He cannot look, cannot aim. One glance around this corner and a bullet erases his face. Yet his hands grip something impossible, and CG-44, with its barrel bent 30 degrees sideways steel, curved like a question mark, a mirror bolted where sights should be. The weapon defies physics. Metal should not bend and fire. Pressure should explode backward through twisted steel. But orders came with 2 spare barrels and a warning: this may save you or kill you itself. His wounded comrade screams somewhere in the smoke. Soviet voices sharpen. Closer. His finger touches the trigger. The curved barrel trembles against his chest. Engineers bent this steel in desperation, forcing bullets to turn corners, gambling that innovation could cheat death. They were wrong about the physics. The barrel will fail. The only question before or after he needs it, one pull decides everything. How do you shoot what you cannot see and survive what should not exist? How did German engineers create a weapon that shoots around corners, and why did physics refuse to cooperate? Late 1943. Germany bleeds territory on every front. Cities become slaughterhouses where stone kills as efficiently as bullets. Urban warfare rewrites every tactical manual. Corners are death traps. Walls are coffins. The soldier who looks dies. The soldier who hides cannot fight back. Tank crews burn alive inside steel boxes overrun by infantry they never saw coming. Soldiers crouch in trenches, heads pressed low, knowing that one glance over the parapet means instant death. Snipers wait. Machine guns traverse. Every exposed inch of flesh becomes a target. The mathematics are brutal and precise. In Stalingrad, Soviet infantry swarmed German armor from blind angles, climbing onto hulls to drop grenades through hatches. In Italy, American forces pinned defenders in buildings where leaning out to return fire equals suicide. The pattern repeats across every contested city. You cannot kill what you cannot see without exposing yourself to be killed first. At Rheinmetall-Borsig in Berlin, engineers stare at casualty reports that read like execution lists. Their eyes burn red from sleepless nights. Coffee goes cold beside blueprints. The numbers tell an unforgiving story. Soldiers die not from poor tactics or weak morale, but from geometry itself. The human body must lean into the open to aim a rifle. Tank guns cannot depress low enough to engage threats at the hull. Physics and anatomy conspire to create killing zones that favor whoever fires first. Wehrmacht command delivers an impossible mandate: solve the blind spot problem or watch more men die predictably. Develop a weapon that allows firing without exposure. Do it now. Do it with steel reserves evaporating daily. Do it while Allied bombers transform factories into rubble. Do it knowing every failed prototype wastes materials Germany can no longer replace. The solution sounds insane the moment someone speaks it aloud. Bend the barrel. Force steel to curve. Make bullets turn corners. Mount these weapons on tank hatches to eliminate blind zones. Attach periscopes so soldiers can aim at what they cannot directly see. Create a rifle that breaks every rule of ballistics but might keep men alive long enough to matter. But steel obeys physics, not desperation. Barrels are machined straight for reasons written into material science. Bullets need linear acceleration and spin stabilization along a predictable axis. Gas pressure explodes to thousands of pounds per square inch in milliseconds. Forcing that controlled violence through a curve invites catastrophic structural failure. The metal will tear itself apart. The engineers know this with absolute certainty. They proceed anyway because the alternative is unacceptable. Every morning brings new reports. More tanks lost. More infantrymen shot dead the instant they tried to return fire. More tactical positions abandoned because defending them meant dying to engage attackers. The curved barrel is madness. But watching men die in predictable patterns while doing nothing is worse. Steel grows scarce. Time compresses. Every day, the front lines move closer to Berlin. Every ruined city adds urgency that drowns rational objection. The project receives authorization not because anyone believes it will work, but because desperation erases the boundary between innovation and insanity. Rheinmetall's engineers face an unforgiving paradox. Solve this problem or more men die. Solve it poorly and the weapon murders its own user. They begin bending steel that was never meant to curve. The first test fires once, then explodes. Engineers mount a curved 20mm barrel to a test frame. One technician pulls the trigger from behind reinforced barriers. The report echoes sharp. Then metal screams. The bullet shatters against the curve's inner surface, fragmenting into razor shrapnel that rips the barrel open from inside. Steel peels backward like torn flesh. Fragments embed in concrete walls 10 meters away. One engineer's hand bleeds from a metal splinter that passed through the observation slot. Evacuation, medical treatment, reset. They modify an STG-44, Germany's most advanced rifle, force a 30-degree bend into the barrel using hydraulic presses and heat treatment. Load it. Fire. The weapon cycles. Again. Again. Hope flickers. By round 50, it still functions. By round 100, microscopic cracks spider through the steel at the stress point. By round 200, the barrel splits longitudinally with a sound like breaking bone. Metal fragments slice the test wall. Another failure. Engineers add reinforcement bands welded around the curve. The barrel survives to 300 rounds. Then fatigue wins. The steel tears open. Progress measures in rounds survived, not problem solved. A 45-degree variant enters trials. Optimism dies quickly. The barrel lasts 160 shots before structural collapse. Accuracy disintegrates beyond 60 meters. Bullets tumble randomly, their stabilization destroyed by the forced turn. Gas vents clog black with carbon fouling because pressure curves no longer match the weapon's engineering. Periscope mirrors, fog opaque from heat and propellant residue. After 3 minutes of sustained fire, the shooter aims blind through gray haze. The weapon survives briefly. Usefulness dies faster. Engineers drill gas relief holes with jeweler's precision, attempting to bleed excess pressure before it ruptures the bend. Blackboards fill with white chalk calculations, pressure curves, stress limits, gas expansion rates, bullet deformation, tolerances. Each variable fights every solution. Fix the pressure problem and accuracy collapses. Fix accuracy and barrel life drops to nothing. Fix durability and effective range shrinks to knife-fighting distance. The mathematics refuse to cooperate. A 60-degree model enters testing. It fires exactly 10 rounds. The barrel buckles catastrophically. Total structural failure. The curve concentrates force beyond what steel can endure at that angle. Physics draws a line and refuses negotiation. Engineers stare at the twisted wreckage and understand they have reached the absolute material limit. The weapon cannot exist at this angle. Not with current metallurgy, not with available alloys, not in this universe's rulebook. Meanwhile, reality accelerates outside the workshop walls. The Eastern Front collapses westward. Allied armor advances faster than blueprints can be revised. Factory floors shake from bombing raids. Sometimes workers draft designs between air raid sirens. Every failed test consumes steel that could forge 3 conventional rifles. Wehrmacht command demands deployable units immediately. The engineers have no solutions, only increasingly desperate compromises painted as progress. They attempt a 90-degree variant anyway, a barrel bent to a perfect right angle, firing directly around corners with 0 exposure. The metallurgy required borders on fantasy. Special alloy steel, reinforced pressure chambers, gas venting systems that belong in experimental labs, not combat zones. Against all logic, it fires in controlled conditions. The weapon functions if functions includes violent bullet fragmentation, unpredictable recoil that bruises shoulders, and barrel life measured in hundreds of rounds instead of thousands. But it works. Somehow. Soldiers can shoot from complete concealment. Tank crews can engage infantry climbing on their armor without exposing themselves to return fire. The tactical implications seem revolutionary. A weapon that cheats death itself. Engineers understand the truth simultaneously. This is not innovation. This is desperation wearing innovation's uniform. A fragile mechanical prayer dressed as breakthrough technology. The weapon operates at the cliff edge of physical possibility. One step further and it plunges into catastrophic failure. Orders still demand 10,000 units for emergency deployment across collapsing fronts. The documented flaws remain unfixable. The steel will fail. The only question is when. What happens when human ingenuity collides with nature's immovable laws? Inside dim Rheinmetall workshops, the fight shifts from battlefield to laboratory. Engineers wage war against physics itself. Every calculation is a move in a chess match where nature never loses. Every solution spawns two new problems. The work proceeds with surgical precision despite its fundamentally absurd premise. Bullet trajectories map millimeter by millimeter through the curved section. Engineers calculate deflection angles accounting for rifling twist rates, projectile velocity, centrifugal forces acting on spinning lead at 3,000 feet per second. The mathematics grow nightmarish. A 30-degree curve deflects the bullet's path while simultaneously destroying its gyroscopic stability. The rifling that normally imparts life-saving spin now fights against intended trajectory. Compensation demands recalculating sight alignment for each single degree of curvature. 1 degree of error at the muzzle means missing by meters at 50 paces. Gas relief holes must position with tolerances tighter than a watch mechanism. Drill them too large and the weapon loses pressure needed to cycle. The next round, the rifle becomes a single-shot dead weight. Drill them too small and pressure spikes fracture the barrel at the bend point during the third magazine. Engineers drill test patterns. Fire. Measure stress fractures under microscope. Recalculate. Drill again. Each iteration consumes hours and irreplaceable materials. The optimal configuration emerges through brutal trial, precisely placed holes, spaced to bleed just enough pressure to prevent explosive failure while maintaining semi-automatic function. The margin for error measures in fractions of millimeters. Periscope sights demand absolute precision that borders on impossible. A single degree of misalignment sends rounds into empty air at 50 meters. 2 degrees and the soldier aims at ghosts, while enemies close for the kill. Engineers machine mirror mounts to tolerances exceeding standard rifle sights. They create a targeting system where shooters aim via reflection judging distance and win through indirect observation while bullets turn invisible corners. Training soldiers to use this effectively means forcing them to unlearn every combat instinct about direct aiming. Muscle memory becomes the enemy. Experience becomes liability. 2 variants crystallize from the wreckage of hundreds of failed prototypes. The Krummlauf PP for Panzer mounts on tank hatches with a 45-degree bend. Its sole purpose: eliminate the lethal blind zone where enemy infantry approach unseen to plant magnetic mines on armor. The weapon fires downward at steep angles, covering the immediate space around the vehicle where main guns cannot depress and machine guns cannot traverse. Effective range 30 meters maximum. Barrel life approximately 300 rounds before mandatory replacement. Tactical value potentially decisive in urban combat where tanks become steel coffins. The Krummlauf II for infantry settles on 30 degrees as the optimal compromise between physics and desperation. Push beyond 30 and accuracy dies. Stay below 30 and the tactical advantage evaporates. At exactly 30 degrees, a soldier fires from behind cover with only the weapon's muzzle exposed to enemy sight. Effective accurate range 100 meters if the barrel maintains structural integrity. Barrel life wildly variable depending on firing rate and maintenance quality, generally 400 to 600 rounds before the steel surrenders to fatigue. Both versions share fatal weaknesses that no engineering can eliminate. Heat concentrates at the bend because curved metal cannot dissipate thermal energy efficiently. The curve becomes a furnace. Fouling accumulates faster where gas flow turns turbulent and deposits carbon like arterial plaque. Cleaning requires disassembly procedures far more complex than standard infantry weapons. Field maintenance under combat conditions with shaking hands and incoming fire borders on fantasy. Replacement barrels must match exact specifications impossible to field produce or improvise from salvage. Engineers draft training manuals thick with warnings. They explain aiming techniques that contradict every training manual. Maintenance schedules that demand attention no combat soldier can provide. Tactical employment doctrine that acknowledges these weapons operate at the ragged edge of reliability. They are temporary solutions to immediate problems, not durable military technology. But temporary solutions matter when the war compresses time itself and men die in the interim. Production authorization arrives 10,000 units total across both variants. Factories adapt despite collapsing resources. Workers machine curved barrels on modified lathes, learning techniques no peacetime gunsmith ever needed. Assembly lines reconfigure overnight. The Krummlauf enters limited manufacture early in 1945, arriving at the precise moment Germany can least afford experimental weapons and most desperately needs any advantage, however fleeting. Can desperation force physics to negotiate? A forbidden frontier, the 90-degree barrel functions in controlled trials. Engineers watch through protective barriers as the weapon fires directly around a corner, the barrel forming a perfect right angle. Bullets emerge perpendicular to the shooter's line of sight. Targets positioned completely out of visual range take hits. The weapon fires from a tank hatch and hits targets completely out of sight. For one brief moment, the impossible becomes real. Then triumph collapses into recognition of what they have actually created. The bullets fragment violently inside the extreme curve. Jacket separation occurs immediately. Lead core and copper casing part company at the bend point. What exits the muzzle is not a stable projectile, but a spray of metal moving in approximately the same direction, lethal up close, unpredictable for the man behind the trigger. At close range, 5 to 15 meters, this proves devastatingly lethal. The fragmenting effect creates a shotgun-like pattern that fills the target area with shrapnel. Against massed infantry in tight urban spaces, it functions almost too well, but predictability vanishes. Each shot produces slightly different fragmentation patterns. Accuracy becomes a statistical concept rather than a certainty. The weapon cannot reliably hit specific targets beyond 20 meters. The periscope sight becomes nearly useless because precise aiming is irrelevant when the bullet disintegrates in flight. What the Germans have invented is not a rifle, but an improvised area effect weapon with a catastrophically short barrel life. Recoil characteristics turn violent and unpredictable. The 90-degree curve disrupts normal recoil forces. Instead of pushing straight back into the shooter's shoulder, energy redirects at angles the weapon was never designed to handle. Mounting hardware loosens after dozens of rounds. The entire assembly shakes itself toward structural failure with each shot. Soldiers test firing the weapon report severe difficulty maintaining control during rapid fire. Heat concentration at the bend point reaches extremes that threaten the steel itself. After 50 rounds of sustained fire, the curved section glows visibly in dim light. Barrel life collapses to between 200 and 300 rounds before the metal fatigues beyond safe use. For context, a standard STG-44 barrel remains serviceable for 5,000 rounds or more. The 90-degree Krummlauf consumes itself at 15 times that rate. Gas venting becomes inadequate at the extreme angle. Pressure spikes back into the action, battering internal components designed for different stress patterns. Extractors break. Firing pins crack. Springs compress beyond their elastic limits and lose tension. The weapon malfunctions not just in the barrel but throughout its mechanical systems. Field armorers report the 90-degree variant requires complete rebuilds after minimal combat use. Engineers stare at their creation and understand the bitter truth. They have pushed metallurgy to its absolute limit and discovered that limit falls short of tactical viability. This is not progress. It is improvisation under duress, a fragile hack dressed as innovation. The 90-degree Krummlauf works in the same sense that a hand grenade works once dramatically and with consequences for everyone nearby. It represents desperation, mathematics trade, long-term reliability for immediate tactical utility, except catastrophic maintenance burdens for momentary advantage. Wehrmacht Command still orders limited production. Orders still demand 10,000 units. Several hundred units enter manufacture despite documented flaws. The Eastern Front consumes men and material so rapidly that even compromised weapons hold value. Tank crews receive P variants for self-defense. Infantry units in Berlin and other urban battlegrounds receive I variants with instructions emphasizing their extreme limitations. But the flaws remain unfixable. How does theory meet reality on the battlefield? Berlin, April. In 1945, the city crumbles under Soviet artillery as street-by-street fighting reduces neighborhoods to skeletal ruins. A Panzer IV crew sits stationary at an intersection engine, idling turret traverse toward the eastern approach. They have been ambushed twice today already. Tank commanders in urban warfare learn quickly or die. Soviet infantry move through destroyed buildings with practiced coordination. They know German tanks cannot depress their main guns enough to engage targets at close range. They know the whole machine gun has limited traverse. They know exactly how to approach from blind angles. Magnetic mines and satchel charges end tank crews regularly. The Panzer IV commander has something the Soviets have not encountered yet. Mounted on his hatch, a Krummlauf P variant with 45-degree bend. The curved barrel points downward, covering the area immediately surrounding the tank, deployed to break an ambush in a narrow street. A periscope allows him to observe without exposing his head. He has fired the weapon only during brief training. Barrel life warnings were emphasized repeatedly. He carries one spare barrel. That is all supply lines could provide. Soviet infantry appear from a demolished apartment block. They move fast and low using rubble for cover, approaching the tank's left side where the turret cannot traverse quickly enough. The commander spots them through his periscope at 30 meters. He squeezes the Krummlauf's trigger. The weapon fires. The curved barrel spits rounds downward and into the unseen, scattering attackers at the approaching infantry. The sound is wrong, sharper, more brittle than standard rifle fire. The attackers scatter immediately, surprised by fire from an angle that should be impossible. Two men drop, the others dive behind a destroyed vehicle chassis. The ambush breaks momentum. For a moment, the line holds. The commander continues firing in controlled bursts. Gas vents hiss. Heat builds rapidly, heat surges. Through his periscope, he watches the barrel start to blur from thermal distortion. Metal groans. After 200 rounds spread across 4 minutes, he feels the weapon's response change. The recoil becomes rougher. The action hesitates between shots. He knows these symptoms from training. Soviet infantry regroup, realizing the fire is limited in arc and duration. They adjust approach angles, probing for the weapon's coverage limits. The commander swivels to track them, firing again. 300 rounds, 400. The barrel temperature exceeds design parameters. The periscope fogs with residue, blurs with residue from heat and propellant. He can barely see his targets now. Visibility collapses to vague shapes moving through gray haze. After a few hundred rounds, the tube finally fractures. 500 rounds. The barrel groans audibly. Metal fatigue approaches critical threshold. He changes to the spare barrel, losing precious seconds during the swap. Soviet infantry close to 20 meters during his reload. He brings the weapon up again, fires, watches the muzzle flash, reflected wrong in his compromised periscope. At 600 total rounds between both barrels, the second tube fractures. The failure happens without warning. A longitudinal crack appears along the curved section. Gas pressure vents sideways instead of forward. The next trigger pull sends a round partially down the barrel where it impacts the fracture point. Metal fragments spray backward, sending splinters of steel back at the gunner. The commander drops into the turret interior, shielding his face reflexively. Steel splinters strike his raised forearm and shoulder. Pain registers immediately sharp and hot. He has been wounded not by enemy fire but by his own weapon pushed beyond what nature permits, wounded not by the enemy but by a weapon pushed beyond what nature allows. Blood runs down his arm. The Krummlauf hangs useless from its mount barrel, split open like a predator's jaw. He collapses wounded not by the enemy but by a weapon pushed beyond what nature allows. The tank crew closes hatches. Main gun engages at point-blank range with high explosive rounds, turning the street into a kill zone that forces Soviet infantry back temporarily. A brief tactical victory dissolves into failure. The tank withdraws, the commander holding a field dressing against his arm, the broken Krummlauf abandoned in place. For 2 brief engagements, the curved barrel worked. It broke an ambush. It saved the crew from the fate other tanks suffered daily. Then physics collected its dead and the weapon destroyed itself while wounding the man it was meant to protect. That night, other tank crews removed their Krummlauf mounts. The tactical advantage does not justify the risk. Most curved barrels never survive long enough to reach combat deployment. Of the 10,000 units ordered, only several hundred are deployed at all. Only several hundred achieve completion before factories fall silent as engineers abandon their stations in the chaos of in 1945. Production facilities suffer bombing raids. Supply lines sever. Workers abandon their stations as Soviet and Allied forces close from multiple directions. The Krummlauf enters service at precisely the moment Germany can no longer support specialized weapons requiring precise manufacturing and regular barrel replacement. Infantry units receiving the I variant report mixed results. Many malfunction, exposing soldiers at the exact moments they need protection. In controlled situations, defensive positions with prepared firing angles, short engagement durations, immediate barrel replacement capability, the weapon performs its intended function. Soldiers fire from complete cover. Casualties from exposure during aiming decrease. The tactical concept proves valid in narrow circumstances, but those circumstances rarely occur in the Wehrmacht's final battles. Urban combat in Berlin and other cities devolves into continuous close quarters fighting. Barrel life limitations become critical. A weapon lasting 400 rounds means little when engagements consume that capacity in a single afternoon. Replacement barrels fail to reach frontline units. Supply chains collapse entirely. Soldiers exhaust their Krummlauf barrels and revert to standard weapons, having gained temporary advantage at the cost of carrying additional weight and complexity. Field reports document malfunctions. Barrels crack prematurely under sustained fire. Periscopes fog and become unusable. Gas vent holes clog with carbon fouling. Extraction failures increase as worn barrels allow excessive pressure into the action. Maintenance procedures prove too complex for field conditions. Armorers lack tools and training to service the weapons properly. Units abandon curved barrels beside roads as dead weight that no longer justifies carrying. Tank crews face similar trajectories. The P variant provides genuine tactical advantage in specific scenarios, defending static positions against infantry assault, covering vehicle approaches during halts in urban terrain. When it works, it fills a critical defensive gap. But reliability issues and limited barrel life mean most tanks revert to conventional defensive measures after initial Krummlauf failures. The weapon cannot sustain the continuous use modern armored warfare demands. Engineers documenting failure modes reach consistent conclusions. The curved barrel operates at the absolute limit of metallurgical possibility. No further refinement can overcome fundamental physics. Bullets require linear acceleration. Barrels require structural integrity along stress lines. Forcing those requirements into conflict produces temporary function at the cost of rapid degradation. The Krummlauf represents ingenuity stretched beyond practical application. Desperation dressed as innovation offers minor tactical relief, but drains precious resources and injures the very men it was meant to shield. By May in 1945, the weapon fades from German arsenals not through combat loss, but through natural attrition. Barrels fracture and remain unreplaced. Units discard the weapons as non-functional encumbrances. A few examples survive as curiosities captured by Allied forces studied briefly filed away in intelligence reports. The curved barrel experiment concludes with a whimper, not because the concept failed entirely, but because reality permitted only marginal success at unsustainable cost. The final accounting shows minor tactical gains purchased with scarce resources during a period when Germany could afford neither. Men died whose deaths the Krummlauf might have prevented. Other men died because resources went toward curved barrels instead of conventional weapons. The calculation offers no clear answer, only the recognition that desperation produces both innovation and waste indistinguishably. What legacy remains from this impossible weapon? The Krummlauf vanishes from active service but survives in memory and concept. Though short-lived, the concept endures. Post-war analysis reveals that despite catastrophic limitations, the core principle held validity. Firing from cover without exposure represents fundamental tactical advantage. The Germans proved the concept feasible even if their execution collapsed under material constraints and physics limitations. Modern militaries study the curved barrel not as successful weapon, but as instructive failure. The line between innovation and desperation becomes clear in retrospect. Engineers pushed steel beyond sustainable limits because tactical necessity demanded attempting the impossible. The attempt failed not from lack of ingenuity, but from immovable physical laws. Metal fatigues, pressure concentrates, heat destroys. No amount of clever engineering circumvents these realities, only postpones their consequences. Contemporary corner-shot systems echo the Krummlauf's core insight while abandoning its methodology. Modern corner-shot systems echo this early attempt to fire without exposure. Israeli military designers developed the corner shot in the early 2000s, a weapon system allowing operators to fire around corners using video cameras and articulated frames rather than curved barrels. The concept proves identical engaged targets without exposure. The execution learns from German failure work with physics rather than against it. Modern systems use straight barrels that pivot mechanically while cameras provide targeting information. Reliability increases dramatically. The tactical advantage the Krummlauf briefly offered becomes sustainable technology. Tank optics and urban combat tactics quietly adopt its principle, see first, risk less. Modern armored vehicles mount multiple camera systems covering every approach angle, eliminating blind spots through surveillance rather than curved weapons. Remote weapon stations allow engagement of close targets without crew exposure. Infantry climbing on tank hulls face immediate and accurate fire from weapons controlled from protected positions inside the vehicle. The problem the Krummlauf attempted to solve finds better solution through electronics and remote operation. Urban combat tactics incorporate the curved barrel's lesson about exposure minimization. Modern infantry training emphasizes using cover effectively, employing mirrors and cameras for observation, coordinating fire from protected positions. Doctrine acknowledges what German engineers learned in 1944, the soldier who must expose himself to return firefights at fundamental disadvantage. Technology serves to minimize that exposure through means more reliable than bending steel into unnatural shapes. Yet the Krummlauf remains a symbol of late-war desperation engineering, sprinting against immovable laws of pressure, heat, and time. Military historians recognize it as symbol of late-war German desperation, a period when tactical innovation accelerated beyond manufacturing capacity, when engineering brilliance could not compensate for material scarcity and strategic collapse. The weapon represents the moment Germany's technical sophistication divorced from practical sustainability. That other nations studied the concept and developed successful descendants validates the insight while highlighting the execution's failure. Museums preserve examples. The Imperial War Museum holds a Krummlauf I variant in climate-controlled storage. The Kubinka Tank Museum displays a P variant still mounted on a Panzer IV hatch. Collectors treasure intact examples. Each specimen tells the same story: human ingenuity can bend steel but cannot escape physics. Innovation under pressure produces both breakthroughs and dead ends. The difference emerges only through testing against reality's unyielding standards. Modern engineers examining curved barrel examples understand the calculations their predecessors attempted. The mathematics were sound. The metallurgy reached available limits. The failure stemmed not from incompetence, but from attempting to extract performance beyond what steel could provide in sustained combat conditions. The lesson endures: technology can stretch nature's rules, but never escape them. Technology cannot force nature's compliance, only negotiate within her boundaries. The Krummlauf's true legacy lives not in museums, but in the principle it validated and the methods it proved inadequate. See first, risk less. Engage without exposure. These remain fundamental tactical truths. The path toward implementing them simply required abandoning bent steel in favor of cameras, remote systems, and working with material limitations rather than against them. In the war's final months, human ingenuity bent steel into impossible shapes. Engineers worked through nights calculating pressure tolerances and stress limits, pushing metallurgy to boundaries nature never intended. Soldiers carried weapons that should not have existed, firing around corners at enemies they could not see. But physics refused to bend with it. Each curved barrel carried within it the seeds of its own destruction, microscopic fractures propagating through steel heat exceeding material limits, pressure battering metal forced into unnatural geometry. The weapons worked until they failed. Failure came rapidly, violently, often injuring those they meant to protect. The Krummlauf stands as a quiet warning: technology can stretch nature's rules, but never escape them. When the alternative is certain death, uncertain weapons hold appeal. When blind spots kill tank crews daily, even a barrel lasting 300 rounds offers value. Innovation under duress produces solutions that peacetime engineering would reject immediately. Yet within desperation lived genuine insight. The tactical problem was real. The solution concept held validity. Modern militaries adopted the principle while abandoning the methodology proof. The Germans identified truth even as they lacked means to implement it sustainably. They saw clearly. They attempted solution with available materials. They failed not from stupidity, but from demanding more from physics than physics permits. The cost fell on hands that pulled triggers. Tank commanders wounded by fragmenting barrels, infantry soldiers carrying weapons that failed at critical moments, engineers who calculated correctly but could not alter fundamental material properties. The Krummlauf wounded its users almost as reliably as it wounded enemies. Technology can stretch nature's rules, test boundaries, push limits, but it cannot escape the laws that govern pressure, heat, and stress. Metal fatigues, barrels crack, bullets fragment. These realities bend for no one, and the cost of trying often falls hardest on those who trusted the innovation enough to point it toward an enemy and pull the trigger. Sometimes the wildest machines weren't madness, they were foresight. But even foresight cannot overcome the unyielding mathematics of what steel can endure and what it cannot.